Hi everybody, it's Dr. Chabot, and in this video we're going to be talking about the electric dipole, which is a really important concept in this semester and in a lot of physics. So first let's talk about what a dipole is. So an electric dipole is simply going to be two equal charges. They have to be equal in magnitude or else it's not a dipole, but they have opposite signs. And those two equal charges and opposite signs are fixed in some way a distance d apart from each other. And that can be in a lot of different scenarios. A common one, for example, would be like some molecules, such as the water molecule is a polarized molecule, and there's some separation between the positive and the negative side of the molecules, and it's kind of rigidly fixed to that distance because of the bonds. So this is our electric dipole, and what we're going to do is now put this electric dipole in an electric field. So I'm going to go ahead then and put this dipole in an electric field. We're not yet going to be talking about the field that the dipole creates, because of course there's a field around this dipole because it's two positive charges. We'll do that in the second part of this video. But in the first part, we're going to be looking and saying, okay, we're taking these two charges and then we're putting them in an external field that's caused and created by some other source charges around, say parallel plates or things like this. So I have some external electric field that these dipoles are in. And now what we want to do is just go back to what happens when we put charges in a field. Well, when we put charges in a field, they experience forces. And again, the electric field now is describing that space. And now we have the actual object of the dipole that is in that space. And so that means that the positive charge on the dipole is going to experience an electric force that's going to be upward, parallel to the field, and the negative charge is going to experience a force that is downward, that's going to go opposite the electric field, and that's again just built into the definition of electric field. And then these are again kind of rigidly attached to each other. So instead of just moving in free space, instead what's actually going to happen is the whole thing is going to twist. So there's the whole dipole will spin in the electric field. And, technically then what that means is that there is a torque on this dipole. So let's look at both of the force and the torque. So first, note that net force, the sum of the force on the dipole is equal to 0 because we have these equal and opposite forces, one force up, one force down. What that means is that the center of mass of the dipole doesn't move. But then there is a torque. But the sum of torques is not equal to 0. And so let's go ahead then and think about what these torques would be, how we can do the torque. So remember that torque can be found from R cross F. And so if I just draw my dipole again, and now I'm actually going to draw it at some angle so that my field and everything isn't exactly aligned. So let's go ahead and draw my plus Q, say here, and then my minus Q over here. And then we can keep our electric field straight up for this. And so then we have this force that's on the positive charge and a force on the negative charge. They have some separation distance d, and their center of mass is going to be located in the center of the two. And so what we have here then is we can start to look at the R in the R cross F. So the R is going to be equal to d over 2, the distance that separates them divided by 2, because it points from the center of mass, the axis that it's going to spin around, to where the force is applied. So if we look at the torque on the positive one, we would notice that it's going to be the magnitude of that R, so that magnitude of R is going to be d over 2 times the magnitude of the force, and the magnitude of the force, remember, is just going to be able to be written as Q times this electric field that it's in, so QE, And then times the sine, because it's a cross product, of the angle between R and F. And so then that's going to, allow us to have some angle between R and F that shows up in that cross product. So the sine of theta. And if we do our right-hand rule, and our right-hand rule, we'll do this a lot more in exam 3, but we take our fingers along the direction of R, as if R is pointing along our fingertips, and then we make it so that our fingers can turn into F. I end up with my thumb pointing into the page, so R across F is into the page, and so that's going to be the direction of our torque. Torque vectors always lie along the axis of rotation and kind of dictate which way something spins around. Now let's look at the torque on the minus charge. So the minus charge is going to also have a torque. It has that force downward on it. And it also has an R. The R points from the center of mass to the location where the force is applied. So its R is also d over 2. Its force is still QE. It's not minus QE because we're doing the absolute value here. So its force is still QE. And then the sine of theta still applies, and it's still the sine of theta. And if we do R cross F for this one, I point my fingers along R, and then I'm actually going to turn them along F. I actually still get into the page. And this makes sense. So even though the forces are anti-aligned, these forces are both working together to spin it in the same direction. So they're working together to spin it, right? So they're working together to spin this dipole. And so we can then get the net torque. The sum of the torques is just going to be these two added together. And so we actually see that the d over 2 goes away, and we simply get here, and I'm going to write this as q times d times e times sine of theta. And I wrote it like that for a reason. And the reason I wrote it like that is because Q and D, these are properties of the dipole itself. Those properties are what charge does it have and how far apart are they. This is our external field that we have no control over as the dipole. It's just whatever field we're put in. And then this here, right, is going to come from the cross product. That's the angle between them. So between Q, D, and E. So what we actually want to do is kind of write this torque now as a cross product. So we can write this useful result that we end up with the torque on a dipole, and we're going to write it as P, I'll define P in a second, cross E. Our E is our external field, so that's going to be our external electric field. That's our torque on a dipole. And what we've done here is we've defined this variable P, and that's going to be equal to our dipole moment vector. So that's our dipole moment vector that has a magnitude of P is equal to Q times D, how much charge is on each one, and then times the separation between them. And by definition, in order to make this cross product work, the P has to point, in this scenario, our P is going to point from our negative to our positive. So negative to positive is the direction of P. So the direction here is built in to the definition of P, and that's created so that this torque equation is the correct order, that it's not E cross P, and that it's P cross E. Now, a nice result of this is that making this definition of the dipole moment vector is that the desired location of the dipole is that the dipole wants to line up with the field. So if we look at the situation here, the P and the E, that would be how it wants to line up. And in terms of where the positive and the negatives are on this, that would be a negative here and a positive here. So my forces would be like this, where the positive is with the field, the negative is against the field. This, because it's how it wants to be, is my stable equilibrium position. So that's my stable equilibrium, and that's going to be my lowest energy state. So that's going to be my lowest potential energy. So we'll talk about the electric potential energy in a second, but generally when things are where they want to be, and you have like a box in a gravitational field and it falls to the ground, that is going to lower energy. So when something is where it wants to be, it's in a low potential energy state. And then we're going to get like our max torque. When our magnetic dipole moment is perpendicular to E, so when there's a perpendicular case there, that's going to be our maximum torque. It'll be the middle energy state, but it's the maximum torque. And then we're going to have, when P is anti-aligned with E, there's going to be temporarily, there will be no net torque on it, but this is going to be an unstable equilibrium. And that is actually going to be my highest potential energy state, because what it's going to turn out is that if I deviate, and if you imagine pushing and twisting this at all from that state, then those forces are just going to flip it all the way around to make it go and come back to its desired state where P lines up with E. And so we can talk about the electric potential energy that's associated with the dipole in this field. And as we saw conceptually, we basically want to have the lowest energy when P and E are aligned and the highest energy when they're anti-aligned. A nice equation for this is simply that we would have U is equal to negative the vector P dot E. And so that's going to be equal to our negative magnitude of P, magnitude of E, times the cosine of the angle between them, because this is our actual dot product, which takes parallel components. If we apply this to these kind of three situations, what we actually see here for our electric potential energy here, my electric potential energy is actually 0 when they're perpendicular to each other, because the dot product equals 0. This is essentially a middle energy state. Now you might think, wait, 0 seems low. Like, how if I have 0 energy, is that a middle energy state? And the answer to that is that, remember that it's not the absolute energy that matters. What matters is a change in energy, and where we call 0 is arbitrary. So think about gravitational potential energy. If I think about here, gravitational potential energy, if I have, the ground, and then I have a building, and then I have, you, or say here on the 3rd floor of the building, some height h above, and then let's say that there's a basement, and then let's put, Bob is in the basement, then all of this kind of, when we talk about the energy, all we know is that you are at a higher energy than the ground, which is at a higher gravitational potential energy than Bob. Where we call 0 doesn't matter. I could call you having 0. We could say that this height here is equal to 0. We could say that this level is 0. And so then these would simply have negative energy. That would just be a negative energy. All that matters is the relative energy. All that matters is the relative energy. 0 is arbitrary. And I emphasize that now because in module 4 we actually have an entire module devoted to thinking about energy. So it's an important concept to start to remember that zero energy is not necessarily our lowest state. So back to our dipole here, we have then that this state of maximum torque when they're perpendicular, the dot product for our energy equation tells us that that's a zero energy state, but it's not as far away from where it wants to be as it could. It's not like I've lifted the box all the way up into the air and I've only just kind of moved it a little bit away from where it wants to go. The highest energy state, in fact, is going to be over here when P and E are going to be anti-parallel. And so if I just go ahead and look at this situation, here my electric potential energy is going to be equal to negative magnitude of P, magnitude of E, and then the cosine of 180, which is negative. So this tells me that my electric potential energy is positive. So I end up with a positive electric potential energy. So this is going to be my most potential energy. Because I end up with a positive value from that equation. And then if we go back to our original situation, when I said this was going to be our lowest energy state, let's verify that that's the case. So my lowest energy state is going to be negative magnitude of P, magnitude of E, and then now the cosine of 0, which is just 1. And so we end up with this one actually being a negative energy. So this one over here has the least energy. It's a negative number. The middle energy is my zero energy. That's just, again, built into the definition. And then the most energy is going to be when it's as far away from where it wants to be as it can get. Okay, so this introduced the idea of the electric dipole, and we put the electric dipole in an external field. We looked at its torque, and we used the properties of the dipole to define this electric dipole moment that talks about how it's going to want to line up in a field. In the next video, we're actually going to look at the electric dipole and the field that it creates around it.